In Visual Studio Code, open up your working directory C++ 17, 20, 23 parallel. Create a new folder 129 rational. Click this button, reduce.cpp, hit enter, Ctrl B. I will copy and paste author Thomas Kim, date 2022 November 9th, Ctrl End, include CPG, rational, HPP, include CPG, STD, extension, void test, GCD, always positive, int main, std, cout, std, bool alpha. Copy this function name, paste it here. We will be using this function. Please Ctrl click. std-gcd is introduced to C++ 17. GCD takes two arguments, m and n. M and n can have different types. Computes the greatest common divisor of the integers m and n. Also returns common type of m and n. If both m and n are 0, returns 0. Otherwise, returns the greatest common divisor of m and n. So, it takes absolute value of m and n. Always positive values are returned. So, this text is very important. Returns greatest common divisor of m and n. Absolute value of m, absolute value of n. It means returned greatest common divisor is always positive number. For example, int n negative 12, int d 3, or g, std, gcd, n, d, std, cout, g equals gcd, n, d, std, and there. Now open up your command prompt. You can open any compiler. cd 129 rational clang std C++20 reduce.cpp ltbb 12 or c.exe, hit enter, clsc. So the returned GCD is positive, n is negative 12, d is positive 3. Now let's move on. Auto reduce tentative. Auto L value reference and auto L value reference D. This is tentative implementation for reduction of rational number n and d. or R over N over D. I will denote Q, where N is numerator, D is denominator. So D can never be 0. We assume D is not 0. This assumption is very important. Now, if D is negative, then N is negative N. D is negative D. Make denominator always positive. Now auto G, SCD, GCD, and D. At this point, D is always positive. So is G positive. But if both N and D are 0, G can be 0. But we assumed D is not 0. So we don't need to check G is 0. We don't need to check this part because we assumed D is not 0. If you scroll up, if both M and N are 0, return 0. Otherwise, returns the greatest common divisor. So, because we assumed D is not 0, we don't need to worry about if G is 0. So, we reduce N by G, D by G. We modified N and D. Then return G. We returned GCD. So this assumption that denominator D cannot be 0 is important. Now void test, reduce tentative. Now here int N, we can put negative 12 or positive 12. Int D, negative 3. Auto G, reduce tentative. Now we pass 12, negative 3. It does not work. We cannot call this function because this is L-value reference. This does not build. To use pure R-value, we have to pass forwarding reference. This is forwarding reference. When auto is used as a function parameter type, it is forwarding reference. In this case, the type of N and D can be either L value reference or R value reference. Now, this is valid. We put N, D. We display Cout GCD N D equals SED Cout G. Or we can say G times N D SED, and there I will give a 2-line break. So we are calling this function here. Now I will disable it. We execute once again. CLSC. Now see 12 minus 3. The GCD is 3. 3 times minus 4. So it becomes minus 12. 3 times 1, it becomes 3. Denominator should always be positive and not 0. Please note that in this documentation, either M or N is not an integer type, or either is possibly CB qualifiable, the program is ill-formed. So M and N should be integral type and not of type bool. We want to constrain this condition. How? This is tentative. Now I copy here, paste. I modify the function name, reduce. Here we have to create some concept. Template, type name P, type name ARG, types. The first template parameter is called prototype parameter. The first template type parameter is called prototype parameter. So P is the prototype parameter. Concept allowed reduce ARG types. Now I use fold expression. Semicolon. Now here SED same as P should be in the ARG types. This is parameter pack. We need operator, then expand parameter pack. This is fold expression. This is not good enough. Template, type name P, concept, allowed type C. Then I will change this function name. Allowed types. I pass here. Then we pass P. We allow short, unsigned short, int, unsigned int, long, unsigned long, long, unsigned long. So we allowed short, unsigned short, int, unsigned int, long, unsigned long, unsigned long. We created a concept. This is not good enough because this P can be reference type or constant type. So from P we have to remove std, remove cb, reft. From P we have to remove constant, volatile, reference, etc. With this we can constrain like this. This is constrained auto. Okay. In this concept, the type of N becomes P. The type of D becomes P. So this P has special status. The first template type parameter is called the photo type parameter. This concept is very important. Now here we want to optimize our algorithm. For example, if the type of D is unsigned, then we don't need to check this part. Okay? So we need using type of D declare type D. This is always L value reference or R value reference. So we have to remove reference. Remove CB reference T. Okay, we have to remove constant, volatile, reference, etc. Then if context for this is compile time expression, then we can find like this. std is signed B. We pass type of D. Okay, so if the type of D is signed integral type, Then we test if d is less than 0. This part is for optimization. Now everything is ready. I will fix like this. Now I copy this again. Copy, paste, reduce, test, reduce, copy, paste it here, disable it. Now this is the same. It should be reduce. Now we can use any compiler. I will say G. This is GNU G++. CLSG. So it works perfectly. Please understand that this reduce function is very important. This function is used to implement rational number. So this function should be extremely optimized. This part is compile time code, so you don't need to worry about this part. This part is executed only when the type of D is assigned integral type. But C++ language generates stack unwinding code for exception handling. If we prevent stack unwinding code for exception handling, we can further improve this function. That is very simple. We can simply put no except. It means we do not need exception handling code in this function, so don't generate stack unwinding code for exception handling. The reason I don't need to worry about exception leak from GCD is that this documentation, control click, says throws no exception. So we don't need try catch. In this function, we don't need try catch. This is the best way to implement reduction function. It is very compact. When d is less than 0, we modify the signs, or we make denominator always positive. Then we take GCD, then we do some division. We don't need to check if G, the greatest common divisor, is 0. We don't need, because we assumed denominator D is always positive. The documentation for GCD says if both m and n are 0, returns 0. Otherwise, returns greatest common divisor. D is not 0, so GCD can never be 0. We don't need to check if G is 0. Now, we will learn how to compare two rational numbers. Void test rational comparison using namespace CPG rational number rational L 7 15. We declared one rational. This is R 11 10. So this is 7 over 15 or 7 over 5 times 3. This is 11 over 10 or 11 over 5 times 2. When we design rational numbers, we have to be very careful for integer overflow. So we want to compare 7 over 15 with 15 over 11 over 10. Okay, we want to compare. We can't do this. We can't 7 times 10 or 15 times 10, 11 times 15, 10 times 15. We cannot compare these two numbers like this way because it can be huge number or it can be huge number or it can be huge number. This does not work. I will copy, paste. Instead of doing this, we have to 5 times 3 over 7, 5 times 2 over 11. So 15 is factored to 5 times 3. 10 is factored 5 times 2. With this, we can compare like this. 2, 7 times 2, 11 times 2. 11 times 3. So we multiplied here with 2. In this case, we multiplied by 3. Now denominators are the same. Previously, it was 150. Now, this is 30. Okay, so this number denominator is much smaller. Also, numerator is much smaller. This numerator is greater than this, or this numerator is smaller than this. So this way we compare these two numbers. How? We need to evaluate. This is G, this is G. Greatest common divisor over 15 and 10. we also need 3 and 2. So we need auto A L has a denominator. Okay, this value is 15. Auto B R M denominator. This R's denominator is 10. Okay, then we factorize like 5 times 3, 5 times 2, like this. Now auto G, we can use reduce function A, B. Now we display LCD Cout A. Previously I say this value is A R M denominator is B. Why we have to copy? Because this function modifies. Then copy this, paste. You can say G times A, B. We fixed our code like this. Now we call this function. Copy, paste it here. I will disable this part. Now let's build once again. CLSG. So 15, 10, 15, 10, 5, 3, 2. So 5, 3, 5, 3, 5, 2, 5, 2. What we need is this value. So auto L M numerator times B auto R M numerator B A. Now we display L R. So we build once again CLSG. So we computed this value and this value. 14, 7 times 2 is 14, 11 times 3 is 33. So we computed numerator 7 times 2, numerator 11 times 3. Now we can compare these two values like this. Auto SO. Now L, we use three-way comparison operator. LCD Cout type of SO, LCD CPG get type category SO std and there. Now std cout SO less than 0 SO less than 0 std and there. Paste SO greater than 0 greater than 0 or SO equal to 0 equal to 0. Now we build CLSG. First, note that the type of SO we used three-way comparison operator. The type is SED strong ordering because the type of L, the type of R, or the type of 7 times 2, the type of 11 times 3 are integral type. So when we compare integral type L and R, the return type is strong ordering. So if this result is less than 0, it is true because 14 is less than 33. SO greater than 0, false. SO equal to 0, false. We haven't defined this operator. Okay, this operator is provided by C++ standard. In my next episode, I will explain how to overload three-way comparison operator. In this episode, I discussed how to use GCD, also how to implement, reduce, how to optimize this function by using keyword no except, also using compile time constructs. This code will be generated and executed only when the type of D is signed integral type. We also learned how to create concept. Using this concept, we constrained the type N. Also, concept and keyword ORO forms constrained ORO. If you learned all these things, especially how to compare rational numbers without causing integer overflow, you learned quite a lot. But if you learned only these things, you learned something very small from this episode. You should have learned how I design this function. When I designed this function, we assumed D is not 0. If we don't assume the denominator is not 0, if we don't assume the denominator D is not 0, this implementation becomes much more complex and much more inefficient at runtime because we have to give error checking code if D is not 0. This is called invariant. This is the way we design C++ library or program. In this book, the C++ programming language, if you search for invariant variant. You can find imposing invariant, invariant, invariant. You can have lots of invariants. Use constructors to establish invariance. What does this invariance mean? Okay, here you can read more about invariance. Such a statement of what is assumed to be true of a class. Once again, what is assumed to be true for a class. In our case, we assumed denominator D is not 0, is called class invariance or simply invariant. This concept of invariant greatly simplify your class design, also your library function design. If you don't read this book, you cannot learn advanced concepts. Learning how to implement this function or how to use move constant volatile reference T, how to use if context per. These things are very small things. Even if you learn these things, you cannot create or design your library properly. In my next episode, I will explain how to overload three-way comparison operator.